is part 2 of our mini-series for the final session. Now, previously we've defined the stability interval of a p-type controller. Now, in this question we will look for 30 degrees overshoot closed loop step responses. And again, we will use the time domain and the frequency domain in order to compare them a little bit and to review these design methods. Now, let's basically start with the frequency domain. Now, since we have 30% overshoot, the first step in calculating a p-type controller is to get the zeta value, the corresponding zeta value. Now, overshoot is equal to 30 divided by 100. Maybe we should put a little bit more on top, to the top. Now, zeta is equal to, and this is very important, in MATLAB we use always log of overshoot divided by the square root of log overshoot pi squared plus log overshoot. You should use it SOS. So in MATLAB we always use log here, but don't be mistaken, because log here in MATLAB does not mean log 10. So this is basically natural log. So when we use log and then have x1, we can immediately see that this is natural log. So log 10 of x1 would give us something else. So this should be equal to 10 in order to have log 10. So we can see that this should be the natural log. So if you use the calculator, be aware of that. And then pi here is basically 3.14. So yeah. Now we have zeta. In order to be able to design a p-type controller or come up with a p-type controller for a certain amount of overshoot, what we should know is that basically the process is the same as looking for the stability interval. So what we've done there was we looked at the argument equals 180 degrees. So argument of g omega should be equal to negative 180 degrees. At that omega star, we're looking for the corresponding k value. Now here, instead of using 180 degrees here, we should note that if we look for negative 180 degrees, we're looking for zeta equals 0, because no damping means that it will oscillate forever. So a little bit damping would get rid of the oscillation eventually, but it will take too much time. If zeta is really, really small, like something like this one here, would take really, really long. Now, the way that the overshoot of a system works is by increasing zeta to a certain point so that we have the corresponding overshoot. Now, increasing zeta would mean that we should move to the left or to a lower angle of the argument of the g omega here. So there's a relation, and the further to the left of 180 degrees you are, the higher will be the zeta value. So the damping would be higher, so you would have less overshoot, basically. And here you start basically with 100% overshoot. So there's a metric that we will need, or a transformation that we will need here for this system in order to work out the required angle here, or the phase. So therefore we need a phase margin, so phi m. And the way to determine this is a bit tricky, but you will have this formula available, so don't be scared of this. So a tan of 2 zeta divided by the square root of minus 2 times zeta squared plus, again, another square root of 1 plus 4 times zeta to the power 4. Now this seems a bit odd, but there's this relation that we have here. Of course, let's get rid of this. Seems okay. So yeah, this is basically the distance that we need to have. Now, of course, A10 returns again radians, so these are basically very important if you use a calculator, because throughout the whole semester we've used logs and we've used A10s, and we didn't mention that you should be aware of if it's radians or if it's degrees. So we can use, for example, A10D to acquire degrees, so you should be aware of that yourself. So this means that instead of using negative 180 degrees, we should add 39 to it. So we should have 39 degrees of distance to end up with 30% overshoot. And that's basically it. At this point, we are almost done, because we know the gain value that we should look for. The only challenge here would be, if you don't have any body plot available, would be to determine the exact point where this happens. So that part could be a bit tricky, but since we have GSS and then plugging in S equals J omega and then having A10 of this part here of the denominator, should help you out in determining it, but then you would have tangent of 100 minus 180 degrees plus phi m. So the tangent of this would be equal to the imaginary part of this divided by the real part of this denominator. And then you should work your way out. So yeah, if it's not a very difficult equation, then you should be able to solve. If it's, then it should be given to you. So we need the point where the phase should be equal to 180 degrees plus phi m, and that's it. Now, how can we get this data? Well, in MATLAB we can use mag and then phase and then omega and then body. So the body function here would give us the data, and then we should use squeeze here in order to get rid of the unnecessary dimensions of these. So, and when you are given a body plot, a sketch of it, then you should be reading on it and be aware that that would be in decibels. So if you get, for example, the frequency, then you would get the gain, and then the gain would be in decibels, so you have to convert it back. So in MATLAB the conversion would be something like this. This is something decibel, let's say minus 3 decibels. So you have to work your way out of this. So divided by 20. So this would be minus 3 divided by 20. And then, since this is log 10, g omega would be 10 to the power of the given value minus 3 divided by 20. So you should calculate basically this in order to convert this into gain, and that would be 0.707. So we skipped these parts too much in our laboratory sessions, so I wanted to mention that. So once we have that, we have to search for the phase. So the phase here should be, so let's say phase D for desired, that should be equal to phase D. So let's get the minimum, the val and index, the minimum of the error here. So that should give us the index here. So omega index, and then the magnitude index, and then the phase index. Index is 28. So We have omega, we have mag. Oh, we don't have mag. So if we have this, if we say mag equals squeeze mag. Oh, we use these. Okay, mag val. We've overwritten the old values, so that's kind of an issue. So there we go. Now we can see that the phase value is 0.7352, which is not correct, which should be phase index. So hopefully this time I'll get it right. There we go. Now minus 180 degrees plus 39 something gives us exactly approximately the phase value that we have here. But since we have the error here, or the value here, it shows that there is a little margin to it. So this means that there will be a numerical error. And this will also be the case for you in the final exam if you have a body plot in front of you on hardcover paper. So you will have a little bit of a reading error into it. So it doesn't really matter that much in the body plot. But if you're using the body plot, you should be careful and aware of that. If you use the numerical way of determining this, then you should be numerically correct, basically. But now, let's see what we have. Now we have the omega value, the magnitude, and the phase value. So basically what we should do is now we should calculate k by taking the inverse of the mag val. And that should be basically it. So it is 1.36. So we can quickly check if it's true or not. And the way that we would do this would be through the feedback command, of course. But you can also check if it's true or not using plain calculations, and I'll show you that. Now, we can use poles and zeros. PZ map, C poles and C zeros, let's say. And then PZ map, and then TS. And we need the poles here. So here we have a pair, and there's a real pole, of course, because if you remember the root locus, two of them were complex conjugates and were moving to the geometric axis, and the other one was moving on the real axis to the left. So the zeta value or the corresponding overshoot would be by through calculating this. Now you can also look for since you have K, since you have GS, you can also have TS here and plug it into this one directly. Since you have the omega value here, you can just plug it in and see if the absolute value and if the phase value correspond to the requirements here. If that's correct, then you're basically done and it should work. But since we're on MATLAB, let's quickly check if we have basically the zeta value that we want to have. So we can basically use, let's see, we have this pole here. This is the real part. This is zeta times omega n, and then plus square root of 1 minus zeta squared times omega n I. Basically, this is what we have here. So here, if we use cosine, since zeta omega n squared, and then this squared and then the square root should give us omega n. So if we use the cosine here, cosine of zeta, so let's say theta, should give us basically the zeta value. So do we have a cos So let's first determine the angle here. Using A10 1.0793 and divided by minus 0.375. So let's see. Of course, here in MATLAB we will have the angle between minus pi and positive pi, but yeah, let's use A10 2D. It should be something like this here. So 109 degrees. And then the cosine D, I guess, should give us this. Of course, this is 109 degrees, therefore we have a negative value, so we might get rid of it by using this, and then this, and we have theta corresponding to this value, which should be basically 0.3579, but it is approximately 0.3282. Of course, there's just one more issue. Now we have calculated the zeta value here, but there's just one more issue. Since this is a third order closed loop, if you look close, we have 3 poles. This will not directly correspond to the overshoot, because our formula here is for second order settling time and overshoot. We have a third order system. This might still work because there's a dominance factor which is sufficiently high enough, because let's say 6.2 divided by 0.37 is approximately 16 times further to the left, so it's really not that big of a deal, but this might not be always the case. So sometimes if you use this relation here, the phase margin relation, you might need to adjust it a little bit. You have to look for the closed loop poles. If you have the zeta value and the dominance factor that works, then you're good to go. But if not, then you might increase it or decrease it a little bit. So this phase D here might be increased or decreased a little bit, depending on the system that you have. So since in the frequency domain we don't take care of the order of the system, how many poles and zeros there are, because we don't talk about them in the frequency domain. So that might cause some issues. Sometimes this relation here might cause some problems. Be aware of that. So now we can basically use step TS and step info TS to get the necessary results here. As you can see, we have overshoot 32.9169, so that's quite good. And we can also see that the overshoot here is kind of what we expected here. So yeah, we basically have what we were looking for. Let's also try to use the time domain approach. Now, using the frequency domain was quite easy. What we've done is we have used the relation between the overshoot and zeta, and then also the relation between zeta and the phase margin, because we were using the phase margin as an offset, and this offset should correspond to our desired overshoot value. So I'll come to the recap later. Let's also try to design that with the time domain approach. So let's say time domain approach. So here it's pretty straightforward. We have GSS and we have sims k. This is a real value. The only thing that we should do is we should construct our closed loop as usual. And as I've already mentioned before, you might stick with the following in order to make stuff easier. You might get the numerator and denominator of your plant, and then PCS should be k times num plus then. This should be directly your closed loop characteristic polynomial. So since you have that, we need another model that will correspond to our desired closed loop. Now, therefore, we know that we will use a set of complex conjugate poles, but we only know the zeta value. This means that we will need a symbolic omega. So that's one of our unknowns. And we will also have a residue pole, let's call it P. Now our desired closed loop polynomial or characteristic polynomial should consist of PDS, which is s squared plus 2 times zeta times omega n times s plus omega n squared, and PES, the product of PDS and PES, s plus p. So let's have this, which should be the multiplication. So what you should do is you should basically plug in zeta value and then take this polynomial and multiply it with this. So let's have PDS times PES. And the problem that we want to address here is to equate the coefficients. So we have PCS, S, and all, and then all the coefficients of PCS should be equal to coefs whole as all. Now let's see what the problem looks like. And we can see that 1 equals 1 appears here. So this validates the fact that the highest order term in PCS and in pole are of coefficient 1. So using VPA prop here will help us a little bit more out. Now we can see that basically 7 equals P plus this here, 6 equals this here, and then we have this one here. So solving for this will be a bit of a problem, because as you can see we have omega n squared, and there is also a multiplication between p and omega n squared. So this is not that easy to calculate. You have to get rid of, for example, p. Therefore, you have to substitute 7 minus 0.7157 times omega n into p in this equation and in this equation, for example. And then you will have only omega n related equation, probably from here. And then you have to get the root of the equation. So it's a hard task to calculate this manually, but it is what it is. And since omega n is not determined, this is basically the hardest version of a algebraic design method, This is basically the toughest case here, since the nonlinearity comes from omega n. All the other terms, if omega n is known, will basically become linear, and it is easy to solve. So keep that in mind. If you have omega n, that will be a bit hard. So instead of knowing the overshoot, knowing the settling time would be much, much easier, because that would somehow get rid of the nonlinearity that comes with omega n. Especially this term here is causing problem, and then this multiplication here. So if you know omega n somehow, or of course both of zeta and omega n, knowing both of them would be even better. So yeah, it is what it is. We have to solve this. So this is the numerical part that you should be aware of, and that will be also time consuming in an exam. So now the life is easy in MATLAB, because you can just call MATLAB solve and then give it the problem, and hopefully it'll solve it for you. So yeah. And it comes with two solutions. Probably one of them will not be used here. So let's see what they are. So kval equals double sol.k, omega val sol.omega, or maybe omega n. And then we have pval. So we have p-val, omega n-val, and k-val. Now, here it is not really necessary to check if p is positive or not, but most of the time it would be a good idea to check if, let's check the problem. So it would be a good idea to check what the condition on p is, but since we don't know what omega n here is, it's not really that much of a big deal. But sometimes it is important to check what the interval for p should be, since if p is negative and you solve for a negative p value, it's just time wasted because you don't really have to check that because it will not work. If the closed loop is not stable, then it doesn't matter if you have a controller that assigns the poles where they should be. So the first step should always be ensuring stability and then try to design. But since this is highly nonlinear, you can skip it for unknown omega n problems. But other than that, keep in mind that you should check for the residue polynomial stability in this problem here. So yeah. So if k-val, p-val, so p-val is positive for both of the solutions, and omega n-val. So we can see that minus 11 is by definition not really what we are looking for, but omega n equals approximately 1 is a solution. So let's have that solution. So let's get rid of the unnecessary stuff here. K-val, before that let me say omega n val should be positive. So all the indices that satisfy that condition should be used, otherwise they should be eliminated. So omega n val and omega n val. So now we had omega val and omega n val, and you can see that they are basically approximately the same. So the omega value that we've used in the body plot is approximately the same as the omega value that we've calculated here. So there's a resemblance here. So yeah, once we've calculated that, we might go ahead and use this k-val and create a figure where we have both step responses. Let's say step, maybe we should call it TS2. So yeah, TS comma black and then TS2 comma, let's say red. The red one is time domain, the black one would be frequency domain. So you can see that there's not that much of a difference, but there's still a bit of a difference. And if we check what the step info now for TS2 is, we can see that the overshoot here is 29.47, which is a bit closer to 30 than the frequency domain was, but yeah, this is basically because of the fact that the frequency domain does not take into account that this is a third order system. Also, the frequency domain here did not result in the best result because we didn't provide it the amount of steps that it should have. For example, if you look at omega, it is logarithmically spaced, but all we care is about omega equals 1 because omega val was approximately equal to 1. So what happens if we narrow the frequency down to 0.01 up to, let's say, 2? Instead of spacing logarithmically, let's increase the accuracy here and see what happens. Now omega val is equal to 0.91 and omega n val is equal to 1.08. And the results are much closer to each other, but still a little bit of a difference. This would be because of the residue pole, because we have a 16 time distanced or dominant complex conjugate pair. So therefore there would be a slight difference, and we can see that. But nonetheless, we can see that using the frequency method is quite easy if you have the necessary knowledge, and the time domain is a bit more time consuming if you try to design a p-type controller just for overshoot. So sticking with the frequency domain would be more time efficient in my opinion. If you have, of course, the settling time and the overshoot, then the time domain would be a bit of a better choice, because we don't really determine the time characteristics in the frequency domain. So keep that in mind. So you could say, you could look at the problem, and if the p-type controller design problem is related to overshoot and overshoot only, you should stick with frequency domain. Otherwise, you can go for the time domain. So we've talked about the zeta and overshoot relation, and then the phase margin and zeta relation, and this was the distance that we should ensure in order to get the required overshoot value, and plug it and looking for the point where the phase angle is exactly equal to this, we get the frequency, and at that point you're almost done. You can plug it into your transfer function and get the polar coordinate representation. And once you have done that, you got the p-type controller, and you can also check if it really satisfies the angle condition that you were after, and then you're basically done. Here we have a low accuracy because we have almost exactly the same result as we've solved it here. So from the time domain approach, you can see that we have to construct this one here, this desired polynomial, and then we have a residue pole, and then multiplying them, getting the coefficients. You can see that step-by-step calculation is a bit tricky. You have also this 0.716 number, which is not really that nice to multiply, but at least you can see that we have to work our way around. Now this is sort of a equation that will give us omega n here. So this is omega n related. So multiplying that with omega n would give us omega n squared at max. So this is a second order equation. You have to use basically the second order root finding algorithm here to get omega n, and then you would plug it in, and everything will be solved here. So that's basically it, and we have almost the same values. The p-type controller is pretty much close to each other, and then the frequency values are also close, and there's this comparison. So that's basically it.